Okay, hello everyone. Thank you for joining us for this HortiQD second webinar, Technology Approaches and MOEMS Fabrication of Near-Infrared Filter Components. So today we will hear three speeches by Professor Carla Hiller and Dr. Christian Elke, so both from Fraunhofer. So what I can tell you is that we will have space for questions at the end of the webinar. So you can ask your question whenever you want, because we have a Q&A section here on Microsoft Teams. You can see it in the bar above. So just click there and write your questions, but note that we will answer the question at the end of the webinar, okay? I will be personally collecting them and ask them to our two speakers. So without further delay, I would leave the word to Professor Carla Hiller. So Carla, the stage is yours with the first speech of today. And if you want to say something before, the speech is titled Working Principle and Application of Tunable Optical Filters. Thank you very much, Carla.
Yeah, hello everyone. I hope you can hear me and you can also see the slides already.
Yes, we can.
Okay, so I have here at the beginning the overview on the three parts of our webinar today, and you see also already myself and Christian, who will be the speaker. And we had the idea to divide this topic, technology approaches and MOEMS fabrication of NIR filter components, in the three parts. So we would like to start with an introduction also of TU Chemnitz and Fraunhofer ENAS, which we represent in this webinar. Then I want to go to the filters and their application and show in the first part some working principles and architectures. Then comes the part from Christian regarding technology, mainly the patterning as a key step. And in the third part, we will show some results for some specific solutions. So not to forget, if someone is asked, where is Chemnitz? What is Chemnitz? In this year, we are the European Capital of Culture. Besides that, we also have a university and also a lot of other research institutes. Two Fraunhofer institutes are situated in Chemnitz, and the Fraunhofer ENAS works very close together with Chemnitz University. We are even situated on the same campus, which is called Smart Systems Campus, where we have, besides the university buildings, including clean rooms, and the Fraunhofer ENAS buildings, including the labs, also companies and other buildings of the university. And regarding the MEMS technology, we run together 3 clean rooms, which have 1,300 square meters of clean room area with ISO 4 to ISO 6, very good conditions for MEMS fabrication. We have the full process line on 6-inch and 8-inch wafers available. And some more details regarding the patterning and lithography will be shown by Christian in the next slides. So this means we can do the full chain from designing elements, fabricating them in our own clean rooms, testing them. We have a lot of tests also in the ENAS building. And so we have very good conditions to cooperate with partners in industry and research. So now I come to the focus of our webinar today, and I want to start with an overview what we have developed at ENAS and ZFM in the last, I would say, 25 years or even more. And already we see a lot of our MOEMS devices, our optical filters, which will be shown in more detail in the next slides. Also micro mirrors, which are situated here. We have also quantum dot based light emitting diodes and also detectors. We have plasmonic structures And this is the component level. This goes then to subsystems and systems, and at least 2 applications I want to show in the slideshow as well. So the first example is a MOEMS spectrometer. What do we want to do with such a spectrometer? We would use light to gather information about a probe. So very famous example is that we have a gas which has specific absorptions depending on which gas composition we have in this probe. So we use a broadband light source, and then this light passes this probe, and then it should be analyzed with regard
Carla, I think we had some audio problem because we couldn't hear you very well, at least the last 10 seconds. So we didn't miss much. Can you try again? Okay, we can hear you well. Thank you. Yes.
Okay.
Better.
So I tried to introduce the principle of such a spectrometer. So we have a light source which passes a probe, and this probe is what we want to analyze. Most famous are gases. Everyone knows that gases have specific absorptions depending on which gas is in this probe. So when the light passes the probe, this information is transferred to the spectrometer. This means it is divided in the frequency or wavelength information of the light spectrum after passing the probe. What do we need for this? We need some elements which can modulate the light, either prisms or gratings, or in our case, an optical filter. And this should have some movable parts. That's why we call it a MOEMS. And then as a result, the light is split either in spatial dimensions and then passed on a detector array, or it can also be in time, separated in time, which is the case for our filter. So at a certain time, only one wavelength can pass the filter, and then we need only one detector, or in this application. So this is how we can analyze the spectrum of a specific probe using such a miniaturized spectrometer. So for what can we use this? In case of gas analysis, for instance, monitor in medicine, anesthesia gases, or in industry, for instance, CO2 measurements, or also for fire and flame detection, or even, if you can see here, for breathing gas analysis as a test for alcohol. Yeah, and this is an example. If you have a spectrum with some characteristic gases here in the wavelength range from 3 micrometer to 5 micrometer, just an example. Then typically, if we have, for instance, a CO2, then we have this typical absorption. And if we have other gases, then we have to look for other wavelengths. And this very small spectrometer is then built out of this infrared emitter, then the sample cell, and this compact tunable filter plus detector. And I would like to talk especially about the filter component. Yeah, example number 2 from the application side, we can also combine the filter with a detector pixel array. So usually we have a camera pixel array, so we see the optical information of a certain probe. If we combine this with a filter, then we can get additional informations from the spectrum. So we take not only one picture, we take a series of pictures with different transmission wavelengths and can get additional information compared to just an optical picture. This is somehow illustrated in this picture from the literature. So, and this is what we want to do in this HortiQD project. Here the application is agriculture. So we would like to have this tunable filter in the near infrared range from 0.8 to 2 micrometer. Want to combine this with a detector array in a camera. And then we want to mount it on a moving device like a tractor or something similar, which can analyze then directly the plants or the fruits, as the apples here in this example. And so we can get information about the health state of this of the plants. So this is the target of this specific application. Yeah, now to come to the device itself. How does this Fabry-Perot filter work? We try to illustrate this here in this small animation. Need to go back. So we have in principle an element which works in transmission. So this means the light passes the filter, and we start with a broadband light source, and then we have an optical resonator with a certain distance in between, and reflectors at the inner side of this reflector cavity. So only one wavelength can pass this filter, which fulfills these conditions depending on the gap size and the order of the spectrum or of the filter. And yeah, for this we need mirrors with high reflection at the inner sides. And we want to have a tunable filter. This means we want to change the distance between these reflectors. And you can see here the transmission characteristics in a certain wavelength range. And this has some characteristic values like the maximum transmission. So 100% would be perfect. We end up maybe in the range of 60 to 70%. Then we want to have a narrow band filter. So this full width at half maximum should be as small as possible to have a good resolution. And we have also some limiting factors, for instance, this so-called free spectral range. So if the order goes higher, we get more peaks. That's a periodic signal, and we can work in one range defined by two neighboring peaks, which somehow restricts the working range of our filter. How can we change the distance between these two reflectors? We use electrostatic drive and also detection of this, and this I show in one of the next slides. So here we see how the transmission wavelength changes if we change the distance. So regarding electrostatic drive and capacitive detection, it's very simple physics what we use here. We have one part of the standard capacitance fixed and the other part movable, connected with a silicon spring. And then we apply a voltage to create electrostatic forces. So this creates a force which acts on the spring, and so we can move this part of the capacitor. And this means finally we can change also our optical distance with this principle. At the same time, we can also use this same arrangement of the two electrodes to measure the capacitance. And this changes when the distance changes. So we have with the same arrangement also the feedback, which cavity size we have in our filter. Yeah, now let's transfer it to the MEMS. how can we arrange this in a MEMS device or MOEMS device. What we see here is a schematic cross-section of such a filter built out of two patterned silicon wafers. This is the upper wafer, which has here the optical reflector carrier in the middle, and here some movable flexible springs. Here we have our reflectors on the movable part, also on the fixed part. And here we have on the lower wafer electrodes where we apply the electrical voltages. And hereby we can create the electrostatic force, which moves down this upper part. Yeah, and hereby we change the optical distance. This means we change the wavelengths which can pass the filter. And below this, we have a detector depending on the wavelength range. In this kind, it can be a pyroelectric detector. And with this, we measure the intensity at the different wavelengths which can pass the filter. Yeah, and the light coming in has already passed this probe, has this already characteristic absorptions depending on which gas is analyzed. So we have designed several filters in order to translate this in MEMS devices. In this section, I just want to show the sketches and highlight some specific things. And later on in the third part of this lecture today, I want to show some technology flows for some examples. So first we developed a design according to this picture, which has one movable part here, and the second part is fixed. And this looks like this. So we see here the same elements, our movable part with the electrode area, the optical area, the movable springs, and some openings for contacts. And this is the second wafer with the fixed part. Here we have the electrode, here we have the optical window. And these wafers are pre-patterned and then mounted together, for instance, in this case by wafer bonding, silicon fusion bonding. With regard to these optical layers, we will also show some details later. This can be different options. In this case, it's distributed Bragg reflectors, which are selective deposited after pre-patterning of the filters. So this first layout has a size of 7 by 7 square millimeters. And yeah, this was one of our first or second approaches in this case. A little bit more simple and with some advantages, we developed then a design where both of the reflector carriers are movable. So both wafers have springs, as we can see here in this schematic cross-section. And again, we have the reflector carrier, we have the optical reflectors. On the outside, we have an anti-reflection coating, and the electrostatic forces is here directly created between the silicon wafers, so they have both electric contacts. The advantage of this approach is that because both parts are movable, they are not so sensitive when we turn the filter within the gravitation field of the Earth. So if one G is applied to both movable parts, then they have the same deflection in the Earth's gravity field. And so we can make this design more sensitive. We can reduce the voltages. And that is why we developed this solution as well. Yeah, and then these filters, which I have shown here, they have silicon carriers, so they are usable for the near infrared range or mid-infrared range of light. And if we want to go to the visible light, then we have to look for other reflector carriers. So in this case, we have, for the lower wafer, we have used glass. And for the upper wafer, we have used membranes, transparent membranes as reflector carriers, either also with Bragg reflectors, or as Christian will show in his part, we can also use sub-wavelength gratings like patterned aluminum or patterned membranes itself. And so we can also provide solutions for the visible range of the light. They also work with capacitive detection and electrostatic drive. So here we have the electrodes directly on the glass and directly on the membrane. And I show also another approach where we have the electrode again on a silicon frame. Yeah, this is more or less established development. So you see, we have several different designs for several wavelength ranges in the near infrared, and also some parameters regarding the resolution and the aperture, optical aperture. Our standard is approximately 2 by 2 millimeters. And also we have some solutions for the visible range of the light, which the cross-section which I have shown before. Yeah, what is new is what we do in this HortiQD project, because here we address an intermediate range, so in the lower end of the NIR spectrum up to 2 micrometer, because we have identified in HortiQD that this range is especially interesting for the effects in our plants which we want to analyze. So we had to find a new approach, because we also target a large optical aperture. And that's why we developed this sketch for a new cross-section. So we have now again a glass substrate with electrodes and with optical layer stack. And the upper wafer is now silicon or silicon dioxide, SOI wafer, which again creates a membrane reflector carrier, which also carries the Bragg layer system. We have also developed a new system. I will say some words in the second part of the webinar regarding to this solution. Yeah, and now the electrostatic drive is between the electrode on the glass and the silicon of the upper wafer. So here you see a sketch how this device should look finally. And I cannot show so much results about this right now, but this is the content of our HortiQD project, and at least I can show some first results in the first regarding the optical layer stacks in the third part of our webinar today. And this is also something which is on our development agenda. What I have shown so far is that the filters work in vertical direction and the detector is placed underneath. We also started some investigations if we try to put this all in plane. This means we have a higher level of integration when we arrange in-coupling elements like shown here, then waveguides with also a movable optical filter in between, electrostatic actor, and then again outcoupling elements and such gas containing cavities where we can analyze the probes. So this is on a lower level of development. So we developed the single elements which need a nano fabrication, so more sophisticated lithography and patterning. But finally, the target is that we can also provide an integrated spectrometer on a chip. And what we see here is that we have also the the optical probing elements to test this integrated filter, both the electrical components and also the light modulation of the light on the ship. Yeah, this is if we cut this ship and also look on the cross section. The first design was made for the mid-infrared, so we have used silicon as a waveguide structure, but also for the electrostatic elements. We can also use an optical fiber to couple in the light. And here you see some more details about these elements. And I think this is the perfect point to hand over to the second part of our webinar today, where Christian will especially describe the lithography and patterning steps which are necessary for this kind of filters, but also for nanostructured surfaces.
Thank you very much, Carla. So I will share my screen. Can you please give a sign that everything you see on slide and hear me quite well?
Yes.
Okay, perfect. So I will explain today some words about different lithography processes, meaning the mix and match process itself, then the grayscale lithography to realize 2.5D and 3D structures, which are really sophisticated for the new application scenarios to get these structures running on wafer level. And at the end, some, as Carla already mentioned, some sub-wavelength structures to get here, for example, the visible fabrication interferometer into the aimed application scenario. So let's start with the mix and match process itself. So mix and match, what does it mean? So from the lithography point of view, there's a really high demand, increasing demand in the fabrication of small and complex patterns in micro-electromechanical systems and also ICs. And for sure, one can use just electron beam writing technologies because they are really flexible, but they need a lot of time. So they are very time consuming, especially, for example, if you need to do the approximation of rounded structures, for example, if you have a variable shape beam writing system compared to Gaussian beam writing with respect to the Manhattan pattern complexity, for example. And so one can assume, for example, if one could decrease the number of exposure time of an electron beam lithography tool by the use of another tool, it should be quite sufficient. Normally it's done in 2 different layers, meaning just do the lithography for the 1 layer, then etch the material below, do the second layer with a somehow overlay compensation, and etch the second layer. One can also do it in one resist layer, meaning writing with the E-beam tool and, for example, another lithography tool in the same resist layer, as one can see it here, for example, E-beam, the yellow one, really small structures, and in our case, for example, an I-line stepper, the larger structures, we expose them both in the same resist layer. So one lithography mask is ready for the structure transfer of the whole pattern of a whole material over the whole wafer. So with this one, you can deal with high resolution. With the E-beam tool itself, you can deal with really fast processing time with, for example, the I-line stepper layouts, for example. And so you can shorten the whole lithographic process, get a lot more wafers running, and especially, which is very important for developing of new material processes, etching processes, you always need a lot of wafers and so a lot of time. And with this approach, you can also fabricate really complex pattern with reduced E-beam time, and so a little bit more flexible, but also really fast. To do some advertisement for my lithography group here in the institute, just 3 of our tools. We have some more, but these are the most sophisticated one. Of the left side, you see our E-beam writer. It's a heuristic tool. It's fully automatic, working after the variable shape beam principle. It's not a Gaussian beam writer, so we have little formats, rectangular or triangular structures or planes, which you will expose in one shot. And so it's somehow really fast and productive system compared to a Gaussian beam writer. And with this, we can resolve 20 nanometer resolution. And of course, for 6, 8-inch special materials, also reticle mask substrate we can handle for this one. So highly flexible and really low CD. In the middle, it's our we always say working horse in our lithography tool clean room. It's a Nikon stepper, an I-line tool going down to 350 nanometer resolution, and again 6-inch, 8-inch, and special material, 6 thin wafers, thin double-side polished wafers, as we have to use it for the fabrication, the ferrometer approach, or also bonded stacks of different wafer compounds going up to 1 millimeter thickness itself. And for example, here the wafer needs just a minute. And for the E-beam, it can take up to 15 hours per full wafer if it's completely exposed with the E-beam itself. And on the right side, we are really lucky that we have since, I guess, 2 years, our fully automatic CT-SAM from Hitachi, where we can characterize and map complete batch of wafers for 6 and 8-inch wafers with a resolution of 2 nanometers. So full wafer characterization about our lithography and also about the process transfer into the material afterwards can be done here for every wafer with a lot of wafers in a certain amount of time. Really, really helpful for the qualification of our own processes and possibilities here. And now going to the real applications for the mix and match approach so far. So at Center for Microtechnologies and Fraunhofer ENAS, we have a so-called photonic integrated circuit platform. This is a 6-inch wafer layout platform for different PIC systems. For example, a wafer consists of 150 dies. One die is shown here in the green schematic, and every die consists again out of single chips here with 72 different PIC systems. Every PIC consists of an, let's see here, our in-coupling structure, then we have a waveguide, then we have an out-coupling structure, and we have a ring resonator. On every die here of these 72 consists of a different configuration, meaning ring resonators 1, 2, 3, 4, different configuration modes or different in and out coupling structures. And so we decided to use this platform for testing the mix and match process from the lithography point of view, because the waveguide here and the ring resonator itself consists always out of 900 nanometer waveguide width, for example. The gap in between is always 500 nanometer or 1000 nanometers, so really nice to have it here with our high throughput I-line stepper lithography tool. But the in-coupling here and the out-coupling structure here, we wanted to test different version of the pattern of arrays, of slanted gratings, or everything there. And so we decided to use the in and out-coupling part with our E-beam itself and to then the etching, and the waveguide and the ring resonator itself is our I-line part. And to show it here, the progress and the limitations maybe for the mix and match approach from lithography side. The whole system as a cross view consists of silicon substrate wafers, of course. Then we have the 1 micrometer silicon dioxide and the 450 nanometer silicon nitride layer, which acts here as the waveguide material itself. And through the PIC platform, we can always do, again, the fully automatically characterization with our CD-SEM, for example. So the resist, which is needed for dealing with mix and match lithography approach, has to be a resist which is sensitive to E-beam, to electrons, and to I-line, to photons, for example. And we use for this case for microsys technologies the NIR EBL 6005, which is a amplified negative tone resist, which can be exposed with the E-beam and the I-line, for example. And the whole lithography process is divided in 3 parts. The first one is the realization of the photoresist layer, meaning we start with a substrate preparation, meaning the iteration bake for 30 minutes at 200 degrees Celsius. Then we perform the spin coating. Here the parameters are there. We spin coated it on 6-inch wafers at 3000 rounds per minute. So that we receive here the 500 micrometer resist thickness, as you can see it here and in the scheme. And then we did the soft bake 3 minutes for 120 degrees Celsius. Then after the photoresist on the wafer, we have to expose the wafers. We started here with the I-line exposure itself because it's high throughput. And again, 25 wafers in, let's say, 30 minutes are done here. And then the whole batch of wafers going to our E-beam tool in vacuum, where every wafer after each other can be exposed overnight or what else. After this, the exposure taking place. So we have to use here a post-exposure bake at 90 degrees for 1 minute. And then we perform the development of the photoresist layer for 1 minute in MRDEF 600, and then doing development and rinsing it in EPA and DI water. First of all, we realized all the experiment for every process, E-beam and I-line stepper itself on our, let's say, CD structures itself. We have for our E-beam tool some special structures where we expose lines and dots, and we could resolve here structures down to 200 nanometer with this resist, with a certain exposure dose of 1.6 microcoulomb per square centimeter, which is quite low. It's nearly near the range of the limit of our E-beam tool itself. So it's really fast photoresist or E-beam resist, let's say this one. And the structures from 200 nanometer starting points or lines look quite well, but below these structures, we have somehow problems with cross linking, even though the exposure dose is already on the lower end of the possible range. So cross linking versus CD, versus thickness itself, everything has to be considered for a stable process. The same was done with our I-line stepper. In the same way, here we have a certain layout which is called tuning fork, where we have even so large width of this fork, which is in the range of 4 micrometer. And then we also have really small ends going down from 300 nanometer up to, again, 2 micrometer. And to see how the dose in a certain resist will influence the resulting CD structure after lithography itself. And we could see here that structures down to 300 nanometer, they are definitely possible, but we have the problem that for negative resist, the cross linking happens with a certain amount of dose. So as you can see, for example, here in this diagram, that just from the, let's say, 800 nanometer structures, we got the cross linking of the resist up to 300, 350 nanometer. This is very important because if the resist is too thin, we cannot etch the structures, for example, silicon nitride above, and this will result in some problems to pattern transfer. Then we tested everything with the real PIC layout, meaning we exposed here waveguide and ring resonators with our I-line tool, and again checked at which certain dose we could reach the structure dimension of, for example, you can see it here with the 900 nanometer of the waveguide width and the ring width, for example. And of course, on the same point with the same exposure dose, you have to deal with the gap in between the ring resonator and the waveguide, for example. So here it is SEM images. The upper part here is the waveguide. It's 900 nanometer, and then you have the 1 micrometer gap to the ring resonator, which is showing here. And so we decided here to go for an optimum dose with 420 millijoule per square centimeter for our I-line stepper process. Then going to the E-beam part itself, which I mentioned, the in and out coupling structures were here the aim in this exposure so far. And the structure we characterized here were the hole array, which consists out of 800 nanometer square holes with a 300 nanometer grading pattern in between. And in electron beam lithography, it's very important to be capital to checking the proximity effect correction, which is caused by the forward and back scattering of the electrons during the exposure with the resist and the material below. So you have always to define certain pack, it's called, based on the resist and the material you use. And so you have different simulation methods to optimize your E-beam process itself. And so just 2 examples shown here. Of the left side, for example, we have chosen our standard proximity effect correction, and you see here the edge of such an array. And for example, if you have a deeper look into the structure itself, you see here round structures, you see cross-linking into the holes itself, so the pack did not work quite well. But with an optimization of the pack itself, you see at the edge clearly sharp photoresist structures. You see really clear the holes inside with no cross-linking. So the dose variation between the edge structures of the layout and the middle structures, and so the dose dependency of the backscattering, for example, was here adjusted in this way, that we have really optimized back and showing really nice structures for this one. And so the structure fidelity looks here really okay, or really good, but on left side was not the case. And also the structure dimension is here, 810 nanometer. The aim was 800, quite okay, but here the structures are quite too small. So by E-beam, one always have to consider everything. And so it's also because it's a really complex process. And then again, we checked if the proximity effect correction was here optimized. Again, we did the same test regarding the dose influence. So at which dose the structure dimension goes in which direction. And as I already mentioned, so 1.6 was the 1.6 microcoulomb per square centimeter was the exposure dose before, where I already mentioned that it's quite in the range of the limit, the lower limit of our e-beam tool itself. So we checked again, starting 1.5 to 1 to 3, for example, in very small steps. And so we resulted here on the CD measurement after the e-beam itself that we here in the range of 1.5 to 1.75 microcoulomb per square centimeter to get really nice structures, meaning here at the edge of this array, and here also in the middle of this array, showing that the structures look nearly the same or quite good the same. So the pack works, and the dose is also in the right way, to showing here really nice structures, which then can be patterned to the silicon nitride layer below. And finally, we got a complete wafer running. It's not just one, there's a lot of wafers are now running through the lithography with this process. So again, a complete 6-inch wafers. Every wafer has 150 chips. One chip is the green one, I already mentioned. And then in the green one, there are the violet ones, 72 different PIC systems. Every system consists of a different configuration. And what's really, really nice to see, the overlapping area, we call it also the stitching area between E-beam and I-line, is somehow critical if it's not really matched. Because if we have an overlay error, the structures are not connected, or the structures are more or less overexposed, again, next to each other. And off the left side here, you see the E-beam part. On the right-hand side, you see the tapered waveguide system, and it matches quite well. It's just an offset here in Y direction, but it's quite small, so everything works quite well. And so for the time aspect, for example, the whole wafer with E-beam, the whole system took 14 hours, despite the fact the photoresist is really, really fast. But if we use the mix and match approach so far, we just needed 3 minutes for I-line. It's very well. It's not so well calculated. In reality, it's just 1 minute, but with handling 3 minutes per wafer, and 2.5 hours in the e-beam tool itself. So quite fast. A lot of wafers in a shorter time can be exposed here, and can be used by our etching colleagues to destroy all of the wafer. Hopefully not. So as a small summary for the mix and match approach, I showed you some results regarding the negative tone resist EMA EBL 6005. Successfully for E-beam and I-line. For I-line, we had a process window of, let's say, 420 millijoule per square centimeter for the waveguide and the ring resonators, with 500 nanometer and 1000 nanometer structures. And for the E-beam, we had an optimized proximity effect correction and PEP, of course. And the dose we needed here is just 1.5 to 1.75 microcoulomb per square centimeter, quite low. The intralevel mix and match approach works quite well. So we showed here wafers with reduced exposure time, but have on the other side, high flexibility to reduce the time, but also get a lot of new structures running, different versions of structures, which is just with I-line not possible in this way. And for the outlook, of course, one have to optimize the stitching, meaning the influence between 2 different exposure tools based on the alignment layer we have to align on. So the marks has to be integrated before. The second part will be some new topic for our institute, I guess, since the last 2 years. We are dealing with grayscale lithography because it's a really, really sophisticated and interesting topic since the last 2 or 3 years. And why is it needed? Because everybody's talking about 2.5D or 3D structures because they are needed for specific MEMS applications. They are needed for photonic structures, for example, lenses, waveguides, optical elements, and all of these other crazy things. And with 3Ds, you need, or you have a more degree in flexible designs, meaning not just 2D binary, because you have also now 3D structures. And if you can deal with 3D structures, you need less lithography steps. So for example, if you can see it here on the right side, you have like a staircase structure of a lens, meta lens, or what else, meaning you have a 3D information into the photoresist layer itself, which then can be transferred to the substrate or to the material below. And what is needed for this one? First of all, you need a resist, which has the capability of dealing with 3D or grayscale lithography, and that does mean that you need a low contrast resist. If you look at this image here, or this graph, for example, you see in red, it's the ideal photoresist, and on the x-axis as exposure dose, meaning at a certain point of light which sees the photoresist, you have all the area of the photoresist is, let's say, exposed and will be in the process of development after this, will be removed if you have, for example, positive photoresist, or remains if you have a negative photoresist after development, meaning that you have a 1 to 0 binary dependency of those to structure afterwards. In green is the real photoresist, meaning you have a high contrast resist, you have this dose is becoming higher, the resist is exposed, and then at a certain exposure dose, all the resist is exposed. So we have not 90-degree, but you have a small slope. And for grayscale lithography, you need the blue one here, which is a low contrast photoresist. This means at every point of a certain dose, the photoresist will expose in a certain, let's say, thickness or layer of the photoresist itself. And this is also seen here, meaning these arrows here, this is small dose, higher dose, and the highest dose here will expose the whole photoresist away. So this is the other point which is needed. You need a low contrast resist, and you need the variation of the exposure dose, for example, as is shown here in these arrows. And how can one deal with this? One possibility is to use direct whiting methods. Since here, for example, electron beam, you can tune every dose with an exposure, or also with direct laser whiting methods. So you can directly modulate the dose to whiting process or exposure process. This means you are highly flexible to dealing here with certain dose at certain layers or structure or areas, let's say this one. But on the other hand, you're quite slow. So one can also think about mask-based systems, meaning here we are dealing with eye-line stable lithography, where you need a mask. And here the key element is the resist, the process itself, but also the mask, because the mask acts here as a modulation layer, meaning that within the mask you have the openings not just in the chromium layer as 0 or 1, but you have the layout you want to expose. It's more or less like a transmittance structure, and so acting this as a dose modulation layer, so that you can also tune the dose, even in the case that you have just one fixed dose per exposure within the eye-line tool itself. And how does it look like, for example? So here is a lens consisting of 64 micrometer in diameter and 8 micrometer height. It looks like this one. This is a fabricated lens of a colleague of mine, consisting of 1900 gray level, for example. And here, for example, is as the mask layout itself look like, meaning you see here on the blue openings that you have a dose modulation on transmittance of the reticle itself or the mask itself by modulation of the opening areas. This is the key. And of course, you also need special resist. And what is also very important, because you need the answer of the photoresist during the dose modulation itself to get this into the model for getting all of this layout data for the transmittance curve itself running, so that you get really the structure you want to have at the end after the exposure. So this is called the contrast curve. This is shown here on this side, which is very, very important, because with this you can tune your 3D structure in the right angle or rounding or whatever you want to have after the end. So again, it's like a dose, which was on the slide before, but here it's called transmission. So 100% transmission, meaning the whole mask is empty, no chromium layer is there, so all of the light goes through. So if we expose with 400 microjoule per square centimeter, for example, 100% transmission, meaning 400 microcoulomb per square centimeter. 50% transmission, for example, meaning then 200 microcoulomb per square centimeter, but that cannot be tuned within the process itself, but with the mask substrate, for example. And so one have to do some contrast curve measurement, dealing, we have a resist with a certain thickness here, and then we expose the whole wafer or the whole photoresist with a certain contrast curve, where the dose is modulated by a transmission in 1% steps, and afterwards one can characterize these and see, okay, in the range here of 25 to 85% transmittance, we have something like a linear fit in between, and so we know 50% transmission will result here in 40% of resist thickness, whereas with 25% transmission, we have nearly 100% resist thickness, and this information goes directly into the modulation of the layout data which is needed for the mask. And with this one can realize the 3D structures quite well. And with our eye-line tool, wafer level processes in high speed, high volume, let's say 1 minute per wafer, you can put every nice, interested 3D structure on the wafer and do not need E-beam or laser direct weighting methods for this one. And so we are going here to some results for this one. For example, with MEMS applications, we have here pyramids. We produced needles. This one, for example, is dose modulation layer, where we printed here 80%, 70, 60, down to 10%, and you see the protest high is enlarging to the top of the resist. It's positive tone resist here in this case, or here small staircase structures in certain transmission percentages here, or side walls which can be tuned, for example, or here again some frostum structures, or even so Fresnel lenses here ready to produce this one. So by I-line, you can use the tools which are already standing in all of the fabs worldwide, because the most of the litho steps are dealing I-line lithography steps. You have an improved design flexibility by this one, going to 2D, 2.5D, and 3D. Again, it's a high throughput process, and you reduce the lithography steps and etching steps, for example, if you can deal everything in one layer. Some points for our photonic group so far, because as I mentioned before, for the mix and match, we are dealing also with waveguide in-coupling, out-coupling structures. And here in this project, we want to address not the sub-wavelength grading structures for in and out coupling, but we want to deal with, let's say, mirror system to couple the light from the top directly into the waveguide itself. And here we tested different angles of the mirrors itself. So what you can see here in the tilted view, to have these structures here, firstly made out of photoresist, but then of course it has to be transferred in the material below. But you can really nice tune the degree and set of freedom quite well to get here really nice structures running for every interesting application so far. And to get here lenses, for example, grading couplers, mirrors, or any 2.5D element of this one. And yeah, this will extend the possibilities of existing photonic platform, for example. So now checking everything with I-line mask-based systems. Now we are going to the same one with E-beam lithography itself. Here the possibility is that you do not need a mask, because you can directly write the certain dose at a certain area or level of the photoresist itself. So here again, I guess you know this one is the negative tone photoresist we also use for mix and match. It's the MOEMS 6005 with 500 nanometer thickness again, and this high sensitivity. I mentioned before the 1.5 microcoulomb per square centimeter. Here we reach this down to 6 microcoulomb per square centimeters to reach the completely high of these 500 nanometer photoresist cross-linked and exposed. Again, gray levels here are realized with, let's say, dose adjustment in between layers. And what is very important, what I forget to mention so far, is shown here on the schematic. For example, for this application, we want to have, let's say, pyramid structures or frostum structures, what else? And to etch it in 500 nanometer silicon dioxide, meaning, first of all, you have to realize 500 nanometer resist, and to deal with the really nice structures into the photoresist layer itself. What, for example, you can see here is in the dose modulation here, a very low dose going up to a very high dose, where you really see the structures coming into the height much more better compared to the left side. And then you have the one in the photoresist layer. And then what is very important, you have to etch the material below. So for example, the 500 nanometer silicon dioxide. And for pattern transfer of 3D or 2.5D structure, it's very important that you etch the material below the photoresist. And on the same side, etch the photoresist away, so that you really can deal with the completely pattern transfer into the material, for example here, the 500 nanometer silicon dioxide, whereas the photoresist is already used, so you do know that you don't have some residuals maybe here on top, and then the whole layout is transferred into the material below. So it's always a trade-off between edge selectivity of the material, edge selectivity of the photoresist itself, and the pattern transfer of the structure, for importance case, the 3D structure into the material below. So it's not done with just one wafer and one process. It's really process development on the needs and specification everybody have with the application or structure so far. And also one critical point is the data preparation itself. In the section before, I mentioned the proximity effect correction in 2D structures. You may think about that it's also the case in 3D, and here it's much more complex because you also have the influence in Z direction. So this all have to be done with the data preparation to getting all of these structures exposed. So here we have with our tool, with Vistic tool, a software package called ePlace, where we are dealing with fracturing, meaning the whole layout you want to produce. For example, here the donuts has to be fractured in Manhattan structures and rectangular and triangular structures, for example. And with the ePlace software itself and the 3D mode, for example, you have to address a certain dose at certain layer. So every color here is another dose and another layer where the photoresist on the same structure is exposed. And then the whole structure is sliced in layers, measured this way or this way, and every dose consists of a certain color and will then result in a different resist height after exposure itself. Here again, some nice images of structures we realized in some experiments so far. And again, here are the pyramids, for example, with 500 nanometer height, and here something about 400 nanometer height. This is everything after etching in 500 nanometer silicon dioxide layers so far. Here we have the donuts and the circle structures, and here again a cross view of the pyramid structures. This is after etching and after lithography, for example, because the pattern consists of the arranged 2 different protest ties of these pyramids. You can see the scan here, and which really lies is the same as showing here. And you see here the 500 nanometer height with a certain angle of the side wall. And here with a lower dose, you could resolve a smaller structures going to 400 nanometer. So in principle, it works quite well. And we are quite happy to go ahead for many, many more fancy structures and layouts from the colleagues and also from the partners. So for grayscale, also a small summary and outlook. So I showed you something about our eyeline grayscale. This is usable with standard eyeline tools and fabs worldwide. It's a high throughput technologies and is somehow the enabler here for new design possibilities by on the same way reducing the process steps and costs to getting 3D running with eyeline. For eBeam, we see it more or less as flexible or rapid prototyping, especially for the case if we do it for near master manufacturing, which is quite often the case, to go here for the replication process with nano-image lithography. And this is somehow the point to go from EBL to high throughput. It's somehow a nice pointing out this. For Outlook, because I already mentioned it, that we use for eBeam the same resist as for mix and match. We are so far testing the results to getting mix and match running with grayscale. There was a talk of a colleague of mine 1 week ago at the Micro Nano Engineering Conference in Southampton. So it's a quite interesting topic. And we have to go for more investigation of high resolution, meaning really smaller CDs, and also to get this process running into the process lines of our industry customers. And for eBeam, it's really, really interesting topic because, as I mentioned, it's already quite flexible. And we have to test here some things to get all the side walls and roughnesses smoothen, but this is also a work which is in progress. There was also a publication from a colleague of mine in the Micro Nano Engineering Journal, I guess 1 month ago. So now coming back to the topic of Fabry-Perot interferometer. This slide was already shown by Carla before, and I will now more focus on the white part, meaning here the nanostructure integration into the small or thin silicon nitride membrane itself, or the metals on the silicon nitride in comparison to the Bragg reflectors. So I guess some of you know that one can use for reflector concept the Bragg reflector itself. All of them consists of high and low reflective index layers as layer pairs with some requirements for the complete technology flow and technology integration in wafer level processes, because you have to ensure layer homogeneity, you have to ensure the structuring of the whole layer stack. The layers you need to integrate has to be compatible with the process itself of wafer handling and everything there, and you have to deal with layer stresses of every single layer. And so, for example, if we go to this example, which we will show now, we would need, for example, a 4-pair layer stack of silicon nitride, silicon dioxide layers, resulting here in a 93% of reflection, for example. On the other side, from simulation point of view, it looks really nice and easy, but for the technology, it's also quite complex because it's nanometer scale, but it shows from the images that you need just 1 or 2 layers. The complexity from this PowerPoint engineering looks less. The stress is just the one material, silicon nitride membrane itself with holes or with the metal stack on it. The performance from a simulation point of view looks nearly the same with 93 to 99% in the spectral range of 560 to 620 nanometer like this one. And in this project, we investigated 2 different concepts. The one is the metals on membrane point. We call it sub-wavelength grading schematic. And the other one is the nanostructured silicon nitride membrane itself. We call it a photonic crystal schematic. The dimensions which are shown here below are for the photonic crystal reflector itself are 436 nanometer holes with, let's say, 100 nanometer in between. And for the sub-wavelength grading reflector, the metal patches consisting of 50 nanometer aluminum on the range of 140 nanometer and a pitch of 200 nanometer. And based on the wafer preparation flow shown by Carla before, and we have to ensure that that our technology integration process goes somehow in parallel with the wafers which Carla mentioned before, so that we have not to realize new complete integration processes. So the main flow, wafer flow of the freestanding membranes are nearly equal to the ones shown by Carla, for example. And so we started also here with 300 micrometers thin double-side polished wafers, where we etch from the backside 250 micrometer cavity into the silicon. This is a batch process, and so we save here a lot of time to the final end of the releasing of the membrane. Then we deposited the material we need, a silicon nitride layer, which acts as the membrane material itself, and some aluminum on the left side acts here as a hard mask for etching, and on the right side for the sub-wavelength gratings, acting as a real material, acting as a reflector itself. Then we performed on the side with the membrane itself the nanopatterning. For the photonic crystals, we used here nano-imprint lithography, and for the sub-wavelength gratings, we used our own e-beam tool. We do the etching of the hard mask aluminum, we do the etching of the silicon nitride layer of the left side here, for example, and at the final end here, we release the membrane, meaning we etch the silicon via a Bosch process from the back side. We move the silicon dioxide, which acts here as an etch stop by the deep reactive ion etching from the back side, and then we move the photoresist on the front side. So in PowerPoint, it looks here like 5 schematics, which are quite easy, but in reality, it's much more complex. Of course, every one of you know this. So here's some results for this one. I will start with the photonic crystal reflector concept, meaning here the nano-imprint lithography approach to getting all of these nano pattern running. Here are some images, and which was here really, really crucial or critical, because we have here the pre-etched cavities on the backside. What you can see here, for example, it's the same layout as for the fabrication interferometer. The mask and the substrates are there, the same usage as I mentioned before, the same process flow. And nano-imprint lithography works that you do perform the wafer with a certain pressure to print the whole wafer. And so every wafer here has just 50 micrometers thin silicon membranes, and one have to find a process to getting these processes running without cracking or destroying the whole wafers by nano-imprint lithography itself. But it works quite well. You see here the front side, this matrix of, I guess it was 8 by 8 of these imprinted nano patterns. Looks really nice. And the pattern transfer in the photoresist layer, if you see it, for example, here on this SEM image view, it looks quite well. You have all of these nice structures of the photoresist, it's the ammonia resist, on the aluminum on the silicon nitride layer itself. Afterwards, everything will be etched. So first of all, we have to open the aluminum hot mask, and in different wafers, we test different process parameters, and this had an influence of the pattern fidelity of course. So for example, you can see it here on the left side. On this wafer, we use this process which ends up in 442 nanometer circle hole diameter, whereas on the right side, it's another wafer. We ended up in 424 nanometer, for example. The aim was here to get 436 nanometer. So we have one above and one below, but it looks really promising. And after the opening of the hard mask, we etched the silicon nitride layer, which you can see, for example, here. And again, we etch down to the silicon dioxide layer, which then at the end will etch from the backside away, so that you have really the freestanding silicon nitride membrane layers with holes in it. All of these things which look here not really nice are some polymers. By doing the etching effect itself afterwards, the holes look really, really nice, much more better. And at the final end, as already mentioned before, we did from the backside here the gray one, which was closed. We did 50 micrometer silicon etching and 1 micrometer silicon dioxide etching, so that the membrane here, which looks just the green one, was then freestanding. And we realized for this 500 0.5 millimeter and 1.0 millimeter apertures, meaning freestanding membranes filled with all of these fancy nanostructural holes. And here again, a wafer from the backside with these cavities and all these colored nanoreflectors apertures. Here a side view, and here some SEM images showing here all of these small holes of this fabricated reflector itself. So it works quite well. And at the end, you see here the structures with the 424 nanometer and the 125 nanometer gap in between. Successfully realized and now have to be integrated into filters. For the subwavelength gratings, this design, as I mentioned, consists of 140 nanometer metal patches on 200 nanometer pitch. We used to have 50 nanometer aluminum on thin silicon nitride membrane. From the simulation point of view, there was the requirement of here these 10 nanometer sharp edges cut it away. But together with the simulation guys, we decided, because it's an e-beam process, it's a wet chemical resist development, there will definitely a rounding. We want to go with thin resist, but then you have this limited selectivity due to etching. There are a lot of discussions has been carried out, and we decided to go through the design as close as possible, meaning that we want to expose rectangular structures, and we use our e-beam with a PMMA resist layer. And that is what we ended after the e-beam litho itself. Again, special point is the critical point of the wafer handling of these thin membranes wafers, meaning again here 50 micrometer thin membranes. These has some drawbacks for our e-beam itself, so we cannot use the pre-aligner, which is very necessary if we want to do layer by layer alignment. We could not use our standard e-chuck for exposure in the tool itself, and some other points, but at the final end, we could resolve structures in the range of 125 nanometer, as you see it here, for example. These black dots are the PMMA resist with a pitch of 190 nanometer. If we look at these table here, we have with 100 nanometer pitch of 200 nanometer and with 124 nanometer to 140 nanometer, not far away from the requirement from simulation point of view. And we decided to go further, meaning that we etch the structures into aluminum afterwards, which then acts as the reflector on the thin silicon nitride membrane of here 150 nanometer thickness. And so you see here a wafer fabricated with all of these patterns. Just these ones here, which are much or more less small, are the reflector apertures. All of the other ones are just test structures for process evaluation and characterization. And this is a SEM image on top view showing the 142 nanometer aluminum patches with a pitch of let's say 193 nanometers. So we are closer to the requirements after the patterning of the aluminum layer itself. At the end, what you can see here, for example, is a freestanding 0.5 millimeter aperture consisting of this thin silicon nitride membrane layer with all of these aluminum metal patches of 140 nanometer CD on it. And after the wafers are all fabricated, I performed some measurements because, which is very, very important, is that all of these reflectors are flat and has a very small warping and also very low roughness. And we measured this with white light interferometer. And we showed here, with, for example, you can see it on the 3D plots, which looks really promising, all of these different colors. But if you see the scale bar here, we we could resolve, let's say, 50 nanometer warping of a whole 500 micrometer large aperture, which is freestanding for the structured silicon nitride layer. And for the ones with the aluminum patches on the silicon nitride layer, we achieved also 60 nanometer on this half millimeter aperture size. Whereas the larger membranes, for example, the nanoporous silicon nitride layers, here we under 1 millimeter, we are in the range of 50 nanometer, which is quite well. And also for the roughness, we achieved here, let's say, 1 nanometer roughness on the whole reflector itself. It's a really promising results. And now I'm coming to the final slide. So the characterization in regarding the reflectance measurement, for example. On the left-hand side, the nanostructured silicon nitride membrane. Of the right-hand side, the metal patches on the silicon nitride layer itself. Again, we wanted to have a reflectance in the range of 570 to 600 nanometer, in the range of 93%, which is comparable to the PREC reflectors. And what you can see here, for example, is that we are in the range here of 93 to 99% reflectance. The green and the black ones, and the blue and the red ones are the two wafers I've showed before with the two different opening diameters of, let's say, 10 nanometer below and 10 nanometer too large. And so it fits quite well to the simulation. We reach a reflectivity in a certain wavelength range, and we are quite happy. And also we could build some filters for this one and achieve the bandwidth of 1.5 to 1.6 nanometer. And for the SVG reflectors itself, we saw here that's really broadband and showing also in the interesting range here to 570 to 600 nanometer reflectance up to, I guess it was 90%. So it will also work in this range. And with this, I will handle again over to Carla because she will show some further results for the other things.
Okay, thank you, Christian. So we have seen already one first technology approaches for the filters with the nano patterned surfaces. But as Christian already mentioned, the integration is still a topic for the future. So nano patterning is difficult enough. So we have reached patterned membranes or patterned nanostructures on the membranes. But as I have shown at the beginning, the filter needs more elements. So we have to integrate the electrodes. We have to establish the optical gap. And that's why for the complete filters, in the width range, we have used still the PREC reflector layers. So I will show this approach a little bit more in detail, and then coming back to the near infrared or mid infrared filters using the silicon reflector carriers. And at the end, I want to show some new results for etalons in this project HortiQD with a new PREC layer stack. So the first point directly starts with the picture from Christian. Now coming back to the PREC reflector solution. PREC reflector means in principle we have alternating layers with low refractive index like silicon dioxide and higher reflective index like silicon nitride. So here the contrast is not so high. That's why we need a double layer stack of 4 layers to get these 93% reflection. So we also tried titanium oxide instead of silicon nitride, which has a little bit higher contrast. So we could save 1 pair of layer stacks. So this is the layout. So here we see the electrode surrounding the optical areas. And you see the membranes is relatively large. Although the optical aperture is in this case also 2 millimeters. So how can we now fabricate the device? So here we see the sketch of the technology. As Christian already said, we start to pre-pattern the upper wafer to have the membranes of approximately 50 micrometer to save some edge time for releasing the membranes later. Then we deposit the membrane material, the silicon nitride, and then it's shown in blue. And also we deposit and pattern this Bragg reflector stack by a combination of wet and dry etching. Here we can integrate now, so it's not so complicated from the lithography point of view. That's why we could further integrate the electrodes and also contact pads to the silicon. And then comes the release etching using the dry etch process so that we have the released membranes. For the lower wafer, as already mentioned, we have a patterned glass wafer where we have the electrodes and also the layer stack, same layer stack as on the membrane. And to get the distance, the optical distance between the two wafers, we used SOA. This is a epoxy which can be patterned by lithography. So we can adjust the thickness by the spin-on, choosing the right material, and the spin-on process needs to be very precise. And then this also serves as a bonding layer between the two wafers. Yeah, you see here some pictures of the realized filters with different membrane sizes, different membrane configurations. And we can also see here, we have really prototypes of the tunable filters. And in this case, it was designed for central wavelengths around 577 nanometers, and especially with the target to have a very small bandwidth in the nanometer range only. And this means we have to use a very high interference order to get this very good results. This means, on the other hand side, that the free spectral range is very small. You see this at the lines of the same colors indicate this free spectral range. Then we have the same periodic signal again. And here it's also shown it depends from the voltage which we apply. So the higher the voltage, then the wavelength goes down, transmission wavelength goes down, and then it repeats for the next order, and so on and so on. So we can choose maybe this working range or this working range, and you see we have a transmission of about 50 to 70% and really a very small bandwidth, which ensures for this specific application a very high resolution. So then some insight in the technologies for the near and mid-infrared based on the designs I have shown before for this first approach, where we have one movable reflector carrier. And for integration of the optical layer stack, finally, we used the selective deposition, but at the beginning, we have also, as shown before, integrated optical layers which were deposited and patterned. So this I show in more detail in the next slides. And we want to mount the wafers together by silicon fusion bonding, because this SO8 has some not ideal characteristics in over temperature and over time. So that's why we wanted to use the direct mounting of the surfaces together. So this means, on the other hand side, we need a precise adjustment, in this case using etch processes to establish the optical cavities. Then bow and roughness, this I show also in detail, are critical because we want to have parallel optical reflectors. And if we use the selective deposition, this I also show in the next slide, then we have a special integration technology to enable this. So some words regarding the optical layer stacks. Again here, I have the design rule. So the product of the refractive index and the thickness of the layer must be a quarter of the central wavelength of the filter. So you can recalculate which thickness you need depending on which materials you choose. So for this 3 to 5 micrometer wavelength range, we have chosen a thermal oxide, a polysilicon, a PECVD oxide, and again a polysilicon as a double layer stack compared to a triple layer stack with the same materials. And the anti-reflection coating in this simple case is just an oxide with a quarter wavelength stack. And this is the reflectance compared to the gold layer. That's why it ends up with 100% here. And we see even for the 2-layer stack, we have about 95% reflection, which is enough for our filter application. 100% would be not so good because then no light can transmit the filter at all. And if the reflection is too low, then the wavelengths or the transmitting wavelength is low, and also the bandwidth of the filter is much wider. The resolution is not so good. So that's why a range between 80 and 95% would be ideal. So more sophisticated designs about these layer stacks are shown here for different working ranges. And also the anti-reflection coating is here much more sophisticated, not just one layer to get the best results. Yeah, and the technology for this approach, we start with depositing the layers. So silicon dioxide and polysilicon are thermal or CVD processes, so the layers are deposited on the whole surface. And using lithography and etching, we remove most of the layers so that they stay only in the area of the optical aperture. Then we have used silicon nitride mask to cover the surface during the wet etching in KOH solution. So we pattern this from the backside. We have different membrane thickness around 50 to 70 micrometer, depending on the design. So we etch until we have adjusted this thickness here. Then we also protect the backside from further etching. And this last etching to get the movable structure can be either wet etching or dry etching. And if we look for the lower wafer, also silicon in this case, we do etching steps to establish both the optical cavity, but also the electrostatic gap. This can be the same, but also can be different. Then again, we do the deposition of this optical layer stack. We protect the outer side to be able to etch selectively the materials and keep a thermal oxide as isolation layer and as bonding surface. And finally, we apply metal on the front side, creating the electrodes, and also on the back side to provide like an optical screen. And then these two wafers are bonded together by silicon direct bonding. So this looks all easy, but the problems come with the influence on the parallel adjustment of the two plates. So any bow would lead to so-called defects. Any roughness would lead to defects, even if the elements are not in the same angle. This would lead to some defects. And also if the light comes not directly perpendicular, but in a certain angle, this also gives some defects. So we have analyzed this for the different influences, and we found that the roughness is not so much a problem. So our deposited layer with a roughness in the range of 1.3 nanometers is fine. But this bow here, it also looks very small, like 36 nanometer over 2 millimeter area, but we found this is already an influence which will give us a certain deviation from the ideal case. So we should keep this as small as possible. This means we have to handle the stress of the layer deposition accordingly. Yeah, and finally we found out that the so-called defect finesse should be in the same order as the reflection finesse, which is mainly defined by the reflectivity of the optical layer stack. So it does not make sense if this is very good and here this is not so good coming from these influences, then the total effective finesse of the filter will be limited by the largest contribution of the failures. So yeah, with this technology, we fabricated filters of this generation with a large chip size, and later on the development went into the direction to shrink this chip size. And so we had this, that this was our last project to create a small filter, only 5 by 5 millimeters, changing from the 1B, one movable element, to the 2B technology. And this is what I want to show in the next slides. So this slide we have already seen. And I also explained already for what it's good to have these two movable reflector carriers. And now again, I want to show some details about the technology. So, which is now identical for the two wafers. So again, we start with creating the cavities, defining later on the optical and the electrostatic cavities. Then we deposit a thermal oxide, which is has influence on the distance between the two layers, but is also at the same time our bonding material. Everything is protected by silicon nitride, and again we do the etching of the membranes. And then the nitride is removed, aluminum is deposited first and patterned, and finally in this case we use the dry etching of the silicon with the Bosch process to get the movable structures and the springs. And now this is the difference to the approaches before. The optical layers are deposited afterwards. So this yellow and orange layers will be deposited in a selective process, which I show in the next slides. Yeah, and finally, the wafers are bonded together by silicon direct bonding. So how does the selective deposition work? So first point is that Jenoptik, it's a company which is can do this with very high precision. So they have a lot of materials available from the near to the mid-infrared range to have the optimum reflection characteristics. And this is a kind of ion assistant evaporation, what they can do. So how can we ensure that we only deposit the material in the range of the optical aperture? We use a mask wafer, which is also a patterned silicon wafer with an opening. And we clamp this wafer together with our wafer, which is pre-patterned. And here we have the tools to do this. So this is a metal basic wafer where we adjust the wafer we want to deposit. Then we have the mask wafer, again in a metal ring. We bring the two rings together. We have to align them using alignment marks, and then they are mounted together in this tool. And this tool we send directly to this company. They do the deposition process, and then we demount everything. And here we see some results. This is the view on the reflector side, and this is the view on the anti-reflective coating side. Area here is 2 by 2 millimeter, so it's not so critical from the alignment point. And this gives us a large flexibility to change the wavelength range by adjusting the materials accordingly. However, the direct bonding is really challenging. If you know what direct bonding means, then you will understand this. You need a particle-free surface. Any particle will not allow a correct bonding. And this is not so easy after a lot of patterning steps, including sending the wafers away. And also, due to this optical layer stack, we have a temperature limit for annealing of only 200 degrees. So we developed a special process for the surface treatment, including mechanical, like a small polishing step, and also special treatment, including plasma treatment before the bonding. But finally, we managed to have this bonding process very good with a high yield. So this is an infrared transmission picture. This bright frame here is the bonding frame. The dark areas are not transparent in this light, and so we can also control the yield of our bonding process. Yeah, and finally, these filters are mounted together with a detector. Here we have a long-term cooperation with the company Infratech in Dresden. So they use our filters, mount them about the detector, and then in such a TO8 housing. And in order to exclude the wavelengths which are not used, they have a wideband filter in this cap. Yeah, and then, as shown at the beginning, they can mount the filters in the spectrometers, very small and portable spectrometers for the shown applications. Yeah, here are some characteristics for this filter in this working range of 3 to 4 micrometer. So here we have used the second or the third order of the filter, depending on which bandwidth we need. And this is very nice characteristics of the filter if no gases are in the optical cavity. And also you see the voltage range for this filter with the two movable reflectors is relatively low. Can be easily integrated in electronics for drive. And yeah, this is our latest development in this field of near-infrared filters, which are established so far. And at the end of this presentation, I mentioned in the beginning in the HortiQD, we want to go to this intermediate spectral range between 0.8 to 2 micrometer. The complete filters are still under investigations, but we did some pre-investigations with fixed filters, which we call etalons. And we also investigated a new Bragg reflector stack because on glass we cannot work with polysilicon because of the deposition temperature. Instead, we investigated amorphous silicon, which can be deposited with a PECVD process. And we, in these pre-investigations, we used two different designs and also established different space here, targeting an order of the second order filter. Yeah, and this is what we got out. So for the lower wavelength range, we have this 70 nanometer amorphous silicon, 160 nanometer silicon dioxide. And for the higher wavelength range, it's 100 nanometer amorphous silicon and 230 nanometer silicon dioxide. Yeah, and depending on the cavities in the different filters, we got out nice transmittance and also good bandwidth of the samples. You see some of them have some variations indicating that the gap size is not uniform. There are some tolerances about this, but finally we could prove that this new layer stack is suitable for further application. So here in this upper wavelength range, we have a lot of work running, so more variants will be created very soon. And at this point, I would like to thank very much Sumanta Srinivasa, our student, who is very engaged in this development and helped a lot in development of these etalons and also in the filters. Yeah, and then with this, I want to come to some summary and conclusion regarding the Fabry-Perot filters. So we think they are very promising components for low cost and small size spectrometers and the hyperspectral imaging. So this is the new topic where we want to bring in our filters. And this is where we work in the HortiQD. Otherwise, for the spectrometers, we have both well-established technologies, but also, let's say, proof of concept and prototypes for visible range filters. We have seen the membrane-based reflectors, nanostructured surfaces. With the integration topic is a bit more challenging and ongoing. And also, I have shown some new concepts for the NIR in this intermediate range, which help us to fill the gap between the established working ranges and with the target to enlarge the optical area to allow a larger area for the detector array to have a high resolution picture at the end for this hyperspectral imaging approaches. So with this, we are at the end of our presentation, and of course, we are ready to answer your questions.
Thank you, Carla. So we received one question during your first speech, and it is by Gokhan Kara, and the question is: thanks for the very interesting talk, Professor Karahiller. Could you expand on the influence of mechanical forces on the spectral accuracy correction needs in the operation of the detector in space, and also on the pixel resolutions that are achievable on an image level? Many thanks.
Okay, so for the last part of the question with the pixels, I think this is still in development. So I cannot give so much details about this. Maybe later in the project we can answer this question better. But for the mechanical stability of these configurations, so we design these filters with respect to the application specification. So this means it's allowed only in the lower nanometer range, maybe 1 or 2 nanometer change in the transmission wavelengths when we turn the filter in the Earth's gravitation field. So like this or like this. And from this specification, we define the stiffness of this filter. And that's why we work with different thicknesses of these springs, depending from this specification. And in case of this filter configuration, both elements are movable, so both will deflect in the Earth's gravitation field. So that's why we think we have an advantage if this specification is very strong. Then maybe it's better to go with this kind of filters, because then both of the reflectors can change accordingly, depending on the outer gravitation field. So does this somehow answer the question? Because it's only allowed a few nanometer change. This is what our previous specification said. And if someone has another specification, we have to rethink and recalculate the stiffness of the springs accordingly.
Okay, Thank you very much for your answer, Carla. So I do not see any other question. So before closing the webinar, I want to remember everyone that this recording will be made publicly accessible to everyone. So check out our website and also our social media. HortiQD project is available on LinkedIn and Facebook, also on Mastodon. So take a look to our social media or our website. And if there's no other question, I would close here the webinar, thanking once again Professor Carla Hiller and Dr. Christian Elke for their help in understanding and discovering more about this subject so strictly related to HortiQD project. So thank you very much. If there are no other questions, I don't see any other questions. So yes, we can conclude here our webinar, and also check out always once again our website, because we will have more events like this in the coming weeks and months. So thank you once again.
Thank you, Claudio.
Thank you.
And if
Goodbye,
everyone
everyone.
has additional questions in the future, you can directly contact us as well.
Yes. Thank you very much, and goodbye, everyone.
Have a nice day. Bye-bye.
Bye-bye.